Everybody, welcome back. We're kicking off a deep dive today into
Ah.
a paper that really shook things up in the AI world.
Yeah.
Especially, I think, for programmers.
Absolutely.
Attention is all you need, it's called.
That's the one.
And it introduces this new neural network architecture called the transformer. And, you might be thinking, whoa, hold on. AI deep dive.
Yeah.
I'm a programmer, not a data scientist.
Right.
But honestly, this paper
Yeah.
is a big deal, even if you don't have a PhD in machine learning.
Yeah. It's a must read, I think, for anyone who works with sequences.
Okay.
So that could be text or code or time series data, anything like that.
So really like any programmer
Yeah.
who's dealing with data.
Pretty much.
Okay.
And the really cool thing about the transformer is the way that it tackles this fundamental problem
Right.
in sequence processing, and that's the limitations of RNNs.
Okay, so RNNs, like these are the old guard of sequence
Yeah.
processing, right?
That's right. Yeah.
They're used a lot in natural language processing.
Yeah.
Understanding the order of words in a sentence.
Mhm.
But what's the issue with them? Why do we need
Uh.
something new?
They process information step by step.
Okay.
So like a line of dominoes falling one after the other.
Okay.
Each step depends on the previous one,
Got
which
it.
means they can be really slow, especially for long sequences.
Okay, so like imagine
Yeah.
trying to analyze like a massive code base line by line.
Right.
It would just take forever.
Yeah, exactly. And that's where the transformer comes in
Okay.
with this radical new approach.
Okay.
It's attention.
Okay.
So instead of processing the sequences sequentially,
Right.
the transformer can actually look at all the elements simultaneously
At the same time.
at the same time.
Wow.
It's like having this global view of your entire code base,
Okay.
and you can instantly understand how different parts connect and relate to each other.
That sounds way faster.
It is way faster.
How does this attention thing actually work?
Yeah.
This sounds like magic.
It does sound like magic,
Yeah.
but it's based on a pretty clever idea.
Okay.
Think of it like searching for something specific in a massive database.
Okay.
You have a query, which is what you're looking for, and you have keys that are associated with each entry in the database.
Right.
And attention basically helps you find the entries that are most relevant to your query.
So instead of sifting through everything, you
Yeah.
can zero in on the important information.
Exactly.
Right.
So in the context of language processing,
Mm-hmm.
each word in a sentence becomes like a query.
Okay.
And it uses attention to figure out which other words in the sentence are most relevant to understanding its meaning.
So it's almost like each word is saying, hey, which other words are my best buddies?
Yeah.
Which ones help me make sense?
Yeah, exactly.
Okay.
So it's all about finding those crucial connections between words,
Mhm.
even if they're far apart in the sentence.
Okay.
That's the beauty of it. The transformer can capture these long-range dependencies that would be really difficult for RNNs to grasp.
Gotcha.
And because it can process everything in parallel, it's blazingly fast
Okay.
compared to those clunky sequential RNNs.
Okay.
We're talking orders of magnitude faster,
Wow. Okay.
especially for long sequences.
So I'm still trying to wrap my head around
Yeah.
how the model actually figures out
Sure.
which words are relevant.
Yeah.
It's not just picking words randomly, is it?
No, it's not random.
Okay.
There's a method to the madness.
Okay.
The transformer uses something called scaled dot product attention
Okay.
to calculate this relevance between words.
All right. Now that sounds
I know it sounds a bit intimidating,
a little bit.
but the core idea is actually pretty intuitive,
Okay.
especially for programmers.
Okay. So break it down for me.
All right.
Like I'm debugging a tricky piece of code.
So imagine each word has this vector representation,
Okay.
kind of like a unique fingerprint that captures its meaning. And to figure out how relevant two words are,
Mm-hmm.
we take the dot product of their vectors.
Okay.
A high dot product means that they're similar. A low dot product means they're not so related.
Okay. That's starting to make sense.
Yeah.
So it's comparing these fingerprint vectors
Right.
to find words that are similar.
Exactly.
Okay, but what's the scaled part about? Why not just use the dot product?
Yeah. So remember how I mentioned that the dot product can be high when words are similar?
Yes.
Well, if the vectors are large, those dot products can get really big really fast,
Okay.
which can cause problems during training.
Uh-huh.
So scaling helps to keep those values in check,
Okay.
makes the learning process more stable.
So it's like normalizing the data
Yes.
and prevent things from getting out of control.
Exactly.
Okay, we do that all the time programming.
All the time.
So we've got these dot products
Yep.
that tell us how similar words are.
Yes.
What happens next?
Okay, so that's where the value part comes in.
Yeah.
So each word along with its vector representation, or its key,
Okay.
also has a value associated with it. Think of the value as the actual information that the word carries.
Gotcha.
Once the attention mechanism has figured out the relevance scores using the dot product, it uses these scores to create a weighted sum of the values.
Okay.
And this weighted sum becomes the new representation of the word, enriched with information from the words that are most relevant to it.
So it's like each word is getting a boost from its buddies,
Yeah.
the words that matter most to its meaning.
Exactly.
And this is happening for every word in the sentence, right?
You got it.
Each word gets to be a query.
That's right.
Find its best buddies.
That's the power of self-attention.
Wow.
Every word gets to be a query, compares itself to all the other words,
Yeah.
updates its representation based on this weighted sum of values.
Okay.
This creates this rich web of connections and dependencies between the words,
Okay.
allowing the model to really grasp the meaning of the sentence as a whole. And it does all of this in parallel, which is what makes it so incredibly efficient.
My mind is officially blown.
Good.
This self-attention thing is seriously impressive.
Yeah.
But I feel like we've only scratched the surface here.
Yeah.
I'm really curious to hear more about this multi-head attention.
Oh, yeah.
I keep seeing in the paper, it sounds like that's where things get even more interesting.
Yeah, things get a lot more interesting.
Okay.
With multi-head attention.
Huh.
So we've got the basics of self-attention down. Each word gets to see how it relates to every other word in the sentence. Now, let's add another layer of sophistication with multi-head attention. Imagine you're trying to understand a complex piece of code. You might look at the syntax, the data flow, the algorithms all at the same time, right?
Yeah.
Well, that's essentially what multi-head attention does.
Okay, so instead of just one attention mechanism,
Right.
we've got multiples running at the same time,
Exact.
each with its own focus.
Yeah.
It's like having a team of expert programmers,
Yeah.
each with their own specialty,
That's a great analogy.
all collaborating to understand the code.
It is, yeah. Each of these attention heads can pick up on different aspects of the input,
Okay.
like the relationships between variables, the flow of control between functions, or even the overall structure of the code.
So it's like having these different perspectives
Right.
all working together to create a richer,
Yes.
more complete understanding.
Exactly. And the transformer uses this multi-head attention in 3 very clever ways.
Lay it on me.
Okay.
What are the 3 ways?
First, there's encoder-decoder attention.
Okay.
This is like a bridge between the encoder, which is the part of the model that understands the input,
Right.
and the decoder, the part that generates the output.
Okay.
Think of it like a communication channel between 2 programmers working on different parts of the same project.
Okay, so the encoder's like one programmer who's analyzing the existing code.
Yes,
Decoder's like another programmer writing new code
exactly.
based on that analysis.
Yeah.
And this encoder-decoder attention helps them to communicate effectively.
Yeah, precisely. The decoder uses this type of attention to focus on the most relevant parts of the encoded input,
Okay.
ensuring that the output is consistent with the information it's receiving from the encoder.
That makes sense.
Yeah.
What are the other 2 ways?
The second way is encoder self-attention. This allows the encoder to look at relationships between words within the input sequence itself,
Okay.
building a deep understanding of how the different parts of the input connect and relate to each other.
So it's like the encoder's having a conversation with itself.
Yes.
Figuring out how all the pieces of the puzzle fit together.
It's like having a team of programmers brainstorming together,
Okay.
each contributing their insights to create a shared understanding of the code.
Okay. And what about the 3rd way?
The third way is decoder self-attention, which is very similar to encoder self-attention.
Uh-huh.
But on the output side, the decoder uses self-attention to make sure that the output sequence that it's generating is coherent and grammatically correct. It's like having a code linter constantly checking your code for errors and inconsistencies as you're writing it.
Oh, wow. Okay. So with these 3 types of multi-head attention,
Yeah.
the transformer can really understand the input,
Yes.
generate a coherent output, and even make sure that the output is consistent with what it was given originally.
That's right.
That's a lot of power.
It is a lot of power, but there's another clever trick up the transformer's sleeve that we haven't talked about yet. Positional encodings.
Positional encodings.
Yeah.
What are those?
So remember how we talked about RNN's processing sequences step by step?
Yes.
Well, that means they inherently understand the order of the elements in the sequence.
Right.
But the transformer processes everything in parallel, so it needs a way to keep track of the order of words in a sentence.
Ah, okay. Because you're looking at all the words at once.
Right.
You need to know which one comes first, second, and so on.
Otherwise, the sentence could lose its meaning completely.
Yeah, for sure.
And that's where positional encodings come in. They're basically these special tags that get added to each word's representation to indicate its position in the sentence.
So it's like adding line numbers to a code file.
Exactly.
So you can refer to specific lines.
That's a great way to think about it, yeah. The transformer uses these positional encodings to maintain the sequential information even though it's processing everything in parallel.
Okay, so I think I'm getting the hang of this.
Good.
But why is all this attention stuff better than using RNNs?
Yeah, that's a great question.
Is it just about speed?
Well, speed is definitely a huge factor.
Yeah.
The transformer can analyze massive amounts of data in parallel,
Right.
which makes it significantly faster than RNNs, especially for tasks like analyzing huge code bases or processing lengthy text documents.
Yeah, that makes sense. Parallelization is always a good thing
It is.
when you're dealing with lots of data.
Absolutely.
But you said there are other advantages too.
Yes. The transformer is also much better at capturing long-range dependencies than RNNs. Remember how we talked about how RNNs process information sequentially?
Yes.
Well, that means they can have trouble remembering information from earlier steps as they move through the sequence.
Yeah, like trying to debug a function where a variable is defined hundreds of lines earlier.
Exactly. It's easy to lose track of what's going on.
Yeah, I've been there.
Yeah. So because the transformer looks at all the elements of the sequence simultaneously,
Right.
it can easily connect words or code elements that are far apart.
Okay.
It's like having a global view of your code where you can instantly see the connections between different parts, even if they're separated by many lines.
So the transformer has a better memory
Yeah,
for long-range dependencies,
it does.
which is crucial for understanding complex code.
Absolutely.
Okay, that's a huge advantage.
It is, and there's one more bonus that I think you'll appreciate as a programmer. The transformer's self-attention mechanism actually makes the model's decisions more interpretable.
Wait, so we can actually see what the model is thinking?
In a way, yes.
That's amazing. How does that work?
By visualizing the attention weights, we can see which words or code elements the model is focusing on when it makes a prediction.
Okay.
This can give us valuable insights into the model's reasoning process and help us understand why it's making certain decisions.
So that's a game changer for like debugging and improving models.
Absolutely. It's
Yeah.
like having a debugger that can tell you exactly which parts of the code the model is paying attention to.
Yeah, that's cool. I can see how that would be really valuable.
Yeah, and this interpretability is one of the key reasons why the transformer has become so popular in the programming world.
Okay, my mind is officially blown. This attention mechanism is seriously revolutionary.
It's pretty amazing.
But before we get too carried away, I want to make sure we understand how this all translates into like real-world results. Does the transformer actually live up to the hype?
It does. The results are pretty mind-blowing,
Okay.
especially when it comes to machine translation.
Okay.
The transformer blew all the previous models out of the water, achieving state-of-the-art accuracy and speed on English to German and English to French translation tasks.
Wow, so it's not just a theoretical concept, it actually works.
It actually works, and they didn't just stop at translation.
Okay.
They applied it to a task called English constituency parsing, which is a fancy way of saying analyzing the grammatical structure of sentences.
Uh-huh.
And guess what? It aced that too.
So the transformer's not just a one-trick pony.
No.
It's like this versatile tool
It is.
that can be applied to all sorts of tasks.
Exactly. And that's what makes it so exciting for programmers. The possibilities are really endless.
Yeah, okay, I'm sold this. Attention is all you need.
Yeah.
Paper
Yeah.
is a must-read for any programmer who wants to stay on top of things.
Absolutely.
But I'm curious to hear your thoughts on how programmers can actually use these ideas.
Sure.
What are some practical applications of the transformer in the world of coding?
Yeah.
I mean, I'm already thinking about, how I could use a transformer to analyze my code,
Yeah.
maybe even like predict potential bugs.
Yeah, absolutely.
That could be huge for code quality and security.
Totally. Imagine like a transformer-based code assistant
Okay.
that can not only identify potential bugs, but also suggest fixes or refactorings.
Oh, wow.
It could learn from millions of lines of code and become like this incredibly powerful tool for developers.
That would be amazing. Like having a super intelligent
Yeah.
pair programmer
Yeah.
who's always like one step ahead of you.
Always one step ahead of you. What other applications can you think of? Think about code search.
Okay.
So instead of relying on simple keyword matching,
Yeah.
we could use a transformer to understand the meaning of code snippets
Okay.
and find the most relevant results, even if they don't share any keywords.
So it's like having a search engine that understands code
Yes.
as well as a programmer.
Exactly.
Okay, that would make finding the right code snippets So much easier.
Way easier.
Who else?
Code generation.
Okay.
We could train a transformer to generate code based on natural language descriptions or specifications. This could dramatically speed up development time and make it easier for people with less coding experience to create software.
Whoa. Okay, so that's getting into some serious sci-fi territory here.
It is, but it's also incredibly powerful.
Yeah.
Imagine being able to say, write me a function that does X,
Yeah.
and the transformer just spits out the perfect code.
That's crazy.
It's not that far-fetched, actually.
Really?
There are already tools that use transformers to generate code, and they're getting better all the time.
This is so exciting. It feels like we're on the edge of a revolution in programming.
I agree, and the best part is this is just the beginning.
Yeah.
We're only just starting to explore the potential of transformers.
Right.
I think we're going to see even more amazing applications emerge in the coming years.
So for all you programmers out there listening,
Yeah.
I highly recommend checking out this Attention is All You Need paper.
Absolutely.
It might seem a little intimidating at first,
Yeah.
but it's worth the effort.
It is.
It's a glimpse into the future of programming. It's a future filled with incredible possibilities.
Yeah, and remember, you don't have to be an AI expert to understand and appreciate the power of attention.
That's a great point.
This is a tool that can benefit everyone, from seasoned developers to aspiring coders.
So go forth.
Yeah.
Explore the world of attention. Play around with these ideas. Experiment with the code.
Have fun with it.
See what amazing things you can create.
Yeah.
Who knows, you might be the one to unlock the next big breakthrough in programming.
That's it for our deep dive into Attention is All You Need.
Yes.
We hope you learned something new and are feeling inspired to explore this exciting new world of AI and programming.
Until next time, keep learning, keep experimenting, and keep pushing the boundaries of what's possible with code.